So today we will begin with spectrum of a matrix. This brings us back to eigenvalues and eigenvectors. We'll do the spectral decomposition theorem first, then graphical interpretation of eigenvalues and eigenvectors, and then Courant-Fisher theorem. I'll state this without proof very briefly. And then if time permits, we will do a little Matlab demo. Okay, so we have a matrix A, which is an n by n, therefore squared, non-defective real matrix. And its eigenvalues and eigenvectors are lambda 1, v1, lambda 2, v2, until lambda n, vn. Since A is non-defective, regardless of the multiplicities of the eigenvalues, there are n linearly independent eigenvectors of A. Therefore, the eigenvectors of A can serve as basis vectors for n-dimensional vector space. Now let's define this matrix. Uppercase V equals v1, v2 until vn. Each of these columns, v1, v2 until vn of uppercase V, is a eigenvector. And since an eigenvector is an n-dimensional vector and there are n of them, V is also a n by n square matrix. Furthermore, since all these eigenvectors are linearly independent, the rank of V is n. Now we have n eigenvalues. We define this matrix lambda, uppercase lambda here. This is a diagonal matrix, diag, lambda I. So its diagonal elements are lambda 1, lambda 2 until lambda n. And the off-diagonal elements of lambda are all 0. So lambda is a strictly diagonal matrix. The spectral decomposition theorem states that this lambda is equal to V inverse AV. A is the original matrix and V is the the matrix formed by the eigenvectors of A, and lambda is the diagonal matrix formed by the taking the diagonal, by taking the eigenvalues of A as the diagonal element. So we have this relationship between sigma, or lambda, B and A. Lambda equals V inverse AV. And A equals V lambda V inverse. So this matrix A can be decomposed into this form also, V lambda V inverse. Okay, so this is the spectral decomposition theorem. And let's see how it works. So this is what we have to prove, the spectral decomposition theorem. Lambda equals V inverse AV and A equals V lambda V inverse. Now, by definition, we know that if lambda 1, V1 are one eigenpair, then AV1 equals lambda 1, V1. Likewise, AV2 equals lambda 2, V2 until AVn equals lambda n, Vn. Now, let's take this V1, V2 until Vn. We arrange the eigenvectors in this fashion. So, and clearly these equalities lead up to this equality here, and you can read it off by AV1. Let's look at the first column on the left-hand side. It's AV1. On the right-hand side, the first column is lambda 1 V1. The second column is AV2, and on the right side, it's lambda 2 V2. But AV1 equals lambda 1 V1, AV2 equals lambda 2 V2. Hence, these n equalities, which are basically from the definition of eigenvalues and eigenvectors of A, lead to this expression. Okay? Now, what is this matrix B1, B2 until Bn? This is nothing but this B here, right? That we defined earlier. Keep that in mind. So we arrive at this expression. Now, this can be factorized as this right-hand side is actually equal to B1, B2 until Bn, this matrix times this diagonal matrix, lambda 1 until lambda n. You can see clearly why. The first column is lambda, so V1 lambda 1, which is lambda 1 V1, plus all these other elements here in the first column are 0. So V2 until Bn, they're all getting multiplied with 0. So we are left with V1 lambda 1, which is lambda 1 V1. The second column here is V1 times 0, then we would have lambda 2, right? So V2 would get multiplied with lambda 2, and every other V here, every other column here, V3, V4 until Vn would be getting multiplied by zeros. So the second column, I don't have lambda 2 written here, but you can see where lambda 2 lies. And so the second column here is V2 times lambda 2, which is lambda 2 V2. And all the way until the last column here is V1 is getting multiplied by 0, V2 will get multiplied by 0. So basically all the eigenvectors here, V1 through Vn minus 1 will get multiplied by 0, except Vn, which gets multiplied by lambda n. So leaving lambda n Vn as the last column. Okay, so this is equal to this. Whence, by definition, this is the matrix that we defined earlier, V, and this is the diagonal matrix of all the eigenvalues of A. Whence, we just showed that AV equals V lambda. Okay? Now, since V is a full rank, this leads to both our statements of the spectral decomposition theorem. If we take this and pre-multiply both sides by V inverse, we have V inverse AV equals V inverse V is the identity matrix, so V inverse V lambda is lambda. So just pre-multiplication with V inverse gives us this statement. On the other hand, post-multiplying with V inverse will, you can clearly see it leads to this statement here. A equals V lambda V inverse. And lambda equals V inverse AV if we do pre-multiplication with V inverse. Any questions?
Oh, it's clear, Dr.
Okay. So now, so this is what we have. Just ignore this slide. I think accidentally some of the slides got swapped. So now let's go for a real symmetric matrix. Previously, it was any real matrix, non-defective, of course. Now we are taking the specific case of a symmetric matrix. Okay, now here, instead of V inverse, we have this relationship. Lambda equals V transpose AV, and A equals V lambda V transpose. So in the symmetric case, I'm replacing V inverse of the earlier spectral decomposition theorem with V transpose in both cases. And so we have to show that V inverse equals V transpose, and then spectral decomposition theorem will lead to these. Okay, all we have to show is that V inverse equals V transpose. Now V transpose V, let's consider that. V transpose is if I take every column of V and take its transpose, and that would be a row of my V transpose, right? So V transpose is V1 transpose, V2 transpose, up to Vn transpose. These are the n rows of my matrix V transpose. And this is my original matrix V. V1, V2 until Vn. Okay? Now let's do the multiplication. We can, although we know that these are matrices, square matrices, we can pretend that they are scalars and do our multiplication. So V1 transpose V1 equals, is in the first column. Now, what's V1 transpose V2? Since the matrix is symmetric, remember we have shown previously that the eigenvectors are mutually orthogonal, correct? The eigenvectors of a symmetric matrix are mutually orthogonal. Remember, everyone?
Yes.
And furthermore, the eigenvectors are all unit vectors. So when we do the multiplication, now each Vi transpose Vj would be a scalar. Okay, so what's V1 transpose V1? Since V1 is a unit vector, V1 transpose V1 is equal to 1, right? Then what's V1 transpose V2? V1 and V2 are mutually orthogonal because A is a symmetric matrix, a real symmetric matrix. So V1 transpose V2 equals 0. V1 transpose V3 will be equal to 0. So V1 transpose V1 equals 1, right? And everything else, V1 transpose V2 until V1 transpose Vn will be equal to all zeros. Now, let's take the second row. So V2 transpose V1 will be equal to 0. V2 transpose V2 will be equal to 1. V2 transpose V3 will be equal to 0 because V2 and V3 are mutually orthogonal. And so all the other non-diagonal elements will be 0 except V2 transpose V2, which shall be equal to 1. So that would be the second row. And we continue all the way to the last row. So last row would be Vn transpose multiplied with each of these column vectors. Vn transpose V1, Vn transpose V2, all the way until Vn transpose Vn minus 1 would give zeros. So we have a bunch of zeros here. The last scalar term entry here would be Vn transpose Vn, which is 1. So this, see, all the off-diagonal elements are zeros, and the diagonal elements of this product, V transpose V, is equal to 1. So the diagonal elements are 1, and non-diagonal elements are zeros. So this is an identity matrix. So V transpose V is an identity matrix. Okay, which means that V inverse equals V transpose, because V is a full rank matrix. If V equals V transpose, it means that V is a unitary matrix. Okay, so we just showed that V inverse equals V transpose. Now we can apply the spectral decomposition theorem. We know that lambda equals V inverse AV. But since V inverse equals V transpose, lambda equals V transpose A. Likewise, A equals V lambda V transpose. This V inverse here is replaced with V transpose. So this finishes the proof of the spectral decomposition theorem and its extension to real symmetric matrices. Real symmetric and non-defective matrices. Okay? Now, let's look at real symmetric matrices a little more. So for a real symmetric matrices, for any real symmetric matrix, if we define this matrix V1, V2 until Vn as the eigenvectors of A, then V would be a unitary matrix. V transpose equals V inverse. Okay? So if A is such a symmetric matrix, then we can represent A in this form. Summation I equals 1 through n lambda I vi transpose. Okay. So we are expressing this matrix A as a sum of different terms, n terms. Each term is lambda I vi transpose. So using the eigenvalues and eigenvectors of A, we are expressing A as a summation. And vi transpose will be a square matrix. Vi transpose vi will be a scalar, as we used here. Each vi transpose vi, or vi transpose vj for that matter, they're all scalars. They're inner products. But this outer product here is vi transpose. That would be a matrix of the same size as A. Moreover, the rank of vi transpose, I'll explain that later, would be rank 1. Each of them will be a rank 1 matrix. Okay, but that's for later. So A equals this summation here, lambda I vi transpose. Proof. We know that A equals V lambda V transpose. We just saw this expression for symmetric matrices, which is equal to, now V is, from our definition, its columns are V1, V2 until Vn, and therefore V transpose is, the rows of V transpose are V1 transpose until Vn transpose, and this uppercase lambda matrix is a diagonal matrix of eigenvalues. Okay, now let's multiply them. Let's multiply the second and third matrices here. Lambda 1, V1 transpose, plus, you know that these are all zeros, right? Plus 0 times V2 transpose, plus all the way to 0 times Vn transpose. So the first row would be lambda 1 V1 transpose. The second row will have all zeros here except lambda 2, right? So lambda 2 will get multiplied with V2 transpose here. So we get lambda 2 V2 transpose. Everything else would be zeros. 0 times, in the second row, 0 times V1 transpose, 0 times V3 transpose, and so on. So the second row is this. And likewise, we continue. In the last row, we have all zeros except for the nth entry here, which is lambda n. So all these zeros will be multiplied with all these v's here. So 0 times v1 transpose, 0 times v2 transpose, all the way until 0 times the last but one row. And lambda n plus lambda n times vn transpose. So it's equal to v lambda n vn transpose. So I multiplied this with this, I got this. Now let's do this multiplication. What do I get? V1 lambda 1 v1 transpose plus v2 lambda 2 v2 transpose. plus, and so on, plus Vn lambda n Vn transpose. But these lambdas are scalars, right? So V1 lambda 1 V1 transpose is the same as lambda 1 V1 V1 transpose. Likewise, the second term would be lambda 2 V2 V2 transpose, and so on. And so this product would be equal to summation lambda I Vi transpose. Therefore, A equals V lambda V transpose. Okay, we proved this property. And this is great because now we are able to decompose the symmetric matrix into three matrices, V, lambda, and V transpose. Okay. Now, as an extension, A inverse equals V lambda inverse V transpose. What are the eigenvectors of the inverse of a matrix? We have seen earlier that the eigenvectors, when you invert the matrix, the eigenvalues, you have to take 1 over the each eigenvalue. Those would be the eigenvalues of A inverse, right? But what would happen to the eigenvectors? The eigenvectors would remain the same. The eigenvectors of A and the A inverse are actually the same. Okay, and at this point, let's do a little demo. So let's go to Matlab. Okay, are you able to see Matlab?
Yes.
Actually, I already have a matrix here. It's a 3 by 3 matrix. Okay, so let me do the eigen decomposition. So VD equals Eig A. And A actually, in my case, is a symmetric matrix. So these are the eigenvectors. Okay, so 0.0169, negative 0.9963, 0.0847 is one eigenvector, and the corresponding eigenvalue is negative 0.3736. Then the second eigenvector is 0.9979, 0.0220, 0.0604, and the corresponding eigenvalue is this 0.587. And likewise, the third column in B is the third eigenvector, and the eigenvalue is this 0.9462. Okay, now let's say B equals inverse of A. Okay, so now let's do the eigenvalues and eigenvectors of this. A inverse. What, so look at this. These are the eigenvalues, right? Now, first eigenvalue of A was this. Okay, and first eigenvalue of its inverse is this. I should have stored the first one. Let's say these. Let's call it VA and DA are the eigen values and eigenvectors of A, and let's say VB and DB are the eigenvalues and eigenvectors of its inverse, which is B. Okay, now this is my VA. Sorry, not B, DA, the eigenvalues of A, and these are the eigenvalues of B. What if I take the dot by element-wise product? dA dot star dB. what would I get?
Identity.
Identity matrix. Oh, they're not arranged in the same order. So 1.05, okay, so let's do this. This is dA, right? And so dB, let me swap the the second and the third eigenvectors. So dB, d temp equals dB 3, 3. I'll store this aside, and dB 3, 3 equals dB 2, 2. So I'm just trying to swap the two eigenvalues. The order is different. It's not following the same indexing as we do. Okay, and then dB 2, 2 equals 10 temporary. And let's look at, this is my dB now, and dA is this. Now dA dot star dB will be equal to the identity matrix. Okay, which shows that the eigenvalues are mutually, multiplicative inverses. Okay, but the eigenvalues would be the same. VA, remember that we swapped the second and the third places, and VB. Okay, you see the first columns are the same, right? Well, ignore the negative. You know, eigenvectors are directions. If you take negative of the eigenvector, it still is an eigenvector. So actually, the first column, both are the same, except one is the negative of the other, right? And the second column here, VA, is equal to the third column here. So that's the same eigenvector. And likewise, the third column here in VA is equal to negative of the second column of VB. So basically, the matrices A and B, which is A inverse, have the same set of eigenvectors. And their eigenvalues are reciprocals of each other. Okay?
Yes.
Okay. Now, let's go back to our slide. Okay, so inverse of a real symmetric matrix. Okay, A inverse is equal to V lambda inverse V transpose. We know that lambda inverse is equal to, how do we invert a diagonal matrix? All we do is take the multiplicative inverses of the diagonal elements. That's what we do with lambda inverse. Lambda inverse contains 1 over lambda 1 until 1 over lambda n. Now, we just proved that A equals V lambda V transpose. Whence, let's take its inverse. A inverse equals V lambda V transpose whole inverse. Open up the parenthesis. We have V. We have to take the opposite ordering when we open up this inverse. So V transpose inverse appears first, V transpose inverse, then lambda inverse, and then V inverse. which is V transpose inverse, because we just saw that V is a unitary matrix, its inverse is its transpose. So V transpose inverse is V, and then we have the second factor is lambda inverse, and then V inverse is, of course, again, V transpose. So A inverse equals V lambda inverse V transpose. Okay. Any question?
No.
Okay. This is pretty straightforward. Now, we can show that square root of A, matrix square roots actually exist, are given by this. B lambda, square root of lambda, B transpose. And square root of lambda is easily defined by taking the square roots of the eigenvectors, because this is a diagonal matrix. So let A half equals V lambda to the half, V transpose. Okay. This is what we have to prove. I'm just working backwards. So I'm assuming this is true, and then I do A half times A half, square root A times square root of A equals V lambda half V transpose, V lambda to the half times V transpose, which is V lambda half. What's V transpose V? Since V is a unitary matrix, V transpose V is the identity matrix, correct? So I'm just ignoring the identity matrix. So V lambda half, then lambda half V transpose, which is equal to V lambda V transpose. If you multiply V to the half with itself, you'll just get back, sorry, lambda to the half with itself, you'll get back lambda. Okay, so this is how we can take the square root of the real symmetric matrix. We can define a matrix exponential. E to the A is equal to, now this is interesting, the eigenvectors are V and V transpose. Okay, this is V transpose because A is symmetric, and E to the lambda is defined like this. Basically, what we are doing is element-wise, we are exponentiating the diagonal elements. Proof is pretty straightforward if we use a Taylor series expansion. E to the A is equal to this, summation k equals 0 to infinity of 1 over k factorial A to the k, with A to the 0 being equal to the identity matrix, by the way, the first term, which is equal to, now replace A to the k with V lambda to the k V inverse. And then you see each term in the summation has V on the left side and V inverse on the right side. So we factor them out, and the middle we are left with summation 1 over k factorial lambda to the k, which is equal to V e to the lambda V inverse. We can define sine and cosine of a matrix in the same manner. E to the A equals sine of the matrix A plus j times the cosine of the matrix A. Okay, and so we can perform any operation on this. We take any operation or any function of A. What we have to do is carry out the same function on the lambdas, and V transpose remain the same on either side. Okay, that's the beauty of this whole thing. So let's say, let's take this example. A equals this. Okay, V, and this is the diagonal matrix of all lambdas, and this is V transpose. Okay, sine of A is that this is V and this is V transpose. They remain the same. And what I've done is taken the signs of the diagonal elements in lambda. Any questions? Okay, now let's look at the geometric view. What do eigenvalues and eigenvectors really mean? Okay. Um, so A is a symmetric, non-defective real symmetric matrix. It could be singular actually, in which case one of the lambdas would turn out to be zero. So its eigenpairs are lambda 1 v1 until lambda n vn. And we arrange the eigenvalues, eigenvectors, we index them such that the numerically the eigenvalue which is highest is lambda 1. Positive or negative, we don't care. Numerically, which is the largest one is lambda 1, and then lambda 2, and then lambda 3, and so on, lambda n. And we know that A equals summation lambda I vi transpose. We saw that before. The VIs are linearly independent and orthonormal, right? Linearly independent because the matrix is non-defective, and orthonormal because it's a symmetric matrix. So now, so that means any arbitrary vector x can be uniquely expressed as a linear combinations of the eigenvectors. So we have n dimensions, n-dimensional Euclidean space, and the v's can act as the coordinates, right, as orthogonal coordinates. Each vi is a unit vector, and all the vi's, the eigenvectors, are mutually orthogonal to one another, right? So they can act as a n-dimensional coordinate system, right? In other words, any vector x in n dimensions can be represented uniquely as a linear combination of these VIs. So let's say x equals alpha 1 v1 plus alpha 2 v2 until alpha n vn. We take any arbitrary x, and so alpha 1, alpha 2, and alpha n are the coefficients for v1, v2, and vn. v1 through vn are the eigenvectors, which are now the coordinates, n coordinates of our n-dimensional space. Okay, so what's the projection? Just a quick question. What's the projection of x onto v1? Since v1 is a unit vector, its projection is simply lambda 1, right? Sorry, alpha 1, right? What's the projection of x onto v2? Simply alpha 2. Do you guys see that?
Yes.
Okay. Okay, so x is expressed in this manner, which is equal to summation I of alpha I vi. Okay. So ax, now let's consider ax. Okay, so this x is this, alpha 1 v1 plus alpha 2 v2 until alpha n vn. Now a, we know that a equals summation lambda I vi transpose. We saw that, right? A is this. So A, the matrix A is equal to lambda 1 v1 v1 transpose plus lambda v2 v2 transpose until lambda n vn vn transpose. Now let's do the multiplication. Okay. This, which is equal to, let's multiply, let's take the summations to the left side. So summation I equals 1 through n, summation j equals 1 through n, lambda I, I'll take the scalars to the left here, lambda I and alpha j, and then vi, vi transpose vj, vi, vi transpose vj. correct? Now, what happens when, um, what's this Vi transpose Vj? If I and j are the same, then if I equals j, then Vi transpose Vj equals 1. On the other hand, if Vi and Vj are different, then what's Vi transpose Vj? 0, right? Because Vi and Vj are all orthogonal. In other words, Vi transpose Vj is equal to the Kronecker delta, delta Ij. Okay, so I replace Vi transpose Vj with delta Ij. And so all I'm left with is Vi. Now look at the summation here. What happens when I and j are different?
0.
0. Delta Ij is 0. Vi transpose Vj is 0, right? So if this is 0, you see all the terms will become 0 except when j is equal to I. Correct? In which case, delta Ij equals 1. All the other terms of this summation vanish. So we are only left with terms lambda I when j equals I. So alpha j becomes alpha I, right? And this becomes 1. Delta Ij when j equals I equals 1. So ignoring it, and this is Vi. Okay? So Ax is equal to this summation lambda I alpha I Vi. X is a linear combination of the V's. The V's are the coordinates, right? And now the product Ax I have expressed as a linear combination of the same coordinates, the same basis vectors, Vi. What are the coefficients? Lambda I, alpha I. If the coefficients of X are alpha I, then the coefficients of Ax, the product, are lambda I alpha I. Okay, that's an important observation. So Ax is given by the summation I equals 1 through n, lambda I alpha I Vi. One quick question. Now, here I originally expressed X in this manner. Now, remembering that V1, V2, all these are unit vectors and they're all orthogonal to one another, right? Then what is the L2 norm or the length of this vector X? I ask you this question. What is the length or the L2 norm of X? It's simply square root of alpha 1 square plus alpha 2 square until until alpha n square, right? If time permits, I can show you a little demo of this one too. Okay. So now this is what I showed, Ax. Okay, now what is the length of Ax? Ax is another vector. What's its length? We can simply take the coefficients and square them, add them up together, and its square root would give you the length of this, correct? So lambda I square, alpha I square, take the summation and take the square root. That would give me the L2 norm of Ax, correct? In other words, Ax, L2 norm of Ax squared is equal to summation lambda I squared, alpha I squared. Okay, now suppose we restrict X to be a unit vector. So X is a unit vector. Okay, which means that summation alpha I squared is equal to 1. Okay. So let's say X equals this. We have this problem given to us. X equals AV1 plus BV2 plus CV3. These are the alphas, alpha 1, alpha 2, and alpha B. I'm just simply writing them as A, B, and C. So the length of X is square root of A square plus B square plus C square. And let's say the eigenvalues of my matrix A are 7, 3, and 1. Okay, I'm just assuming. I have some A whose eigenvalues are 7, 3, and 1. So AX is 7AV1 plus 3BV2 plus CV3. The length of AX is same as the L2 norm of AX, which is equal to square root of this. 7A whole squared is 49A squared. 3B whole squared is 9B squared. C squared is here. And we take the square root of that. That's the length of AX, correct? I want to maximize X subject to this, X equals 1. So I want to maximize the length of AX. What do I do? Under this constraint, X equals 1. How do I do that? Since the length of X equals 1, I must satisfy A square plus B square plus C square equals 1, correct? A square plus B square plus C square equals 1. And I want to find scalars A, B, and C such that this A square plus B square plus C square equals 1, that will maximize this length of AX. How do I do that? In other words, this A square plus B square plus C square should be equal to 1. And I want to pick ABC such that 49A square plus 9B square plus C square is maximum. I simply you see the coefficient here is 49, right? If I let A equals 1 and B and C equals 0, so it satisfies A square plus B square plus C square equals 1, right? If A equals 1, then what's the length of this AX? Square root of 49A squared. 49, if A equals 1, this is 7, right? 49 times 1 plus 9 times 0 plus 9 times 0. So square root of 49 is 7. So the maximum value of L2 norm of AX is 7. Okay. And what do I do is V1 is the first eigenvector, which corresponds to the largest eigenvalue of A. Second largest eigenvalue is 3, and our corresponding eigenvector is V2, and so on. All I do is make X equal V1. That maximizes the length of AX. This is just a small example. So in general, suppose I want to maximize the length of AX subject to X being a unit vector, L2 norm of X equals 1. This is my problem. What do I do? Alpha 1 equals 1. I let alpha 1 equals 1 and all the other alphas equal 0. So V1 equals, in other words, summarizing this observation in this form, V1 equals argmax with X being restricted to a unit vector of L2 norm of AX. Am I clear with this?
Yes.
Okay. What's X here in this, when I do this maximization, X turns out to be equal to V1, right? Just like here, X with A equals 1 and B and C being equal to 0, X will turn out to be V1. here, V1 is argmax over all unit vectors x of L2 norm of AX. Okay, so this is important for you guys to understand. And what's the length? Now here, what happened to the length of AX? The length of AX was simply 7, right? When x was equal to V1, the length of AX was equal to 7. Okay, so the length would be, excuse me, it was equal to 7. So the length, the maximum length of AX with x being a unit vector is lambda 1. Okay, so I hope you understand these two. This is very important. Now, so this is what we have. Now let's look at this problem. This is our x, and we are restricting ourselves to unit vectors. Okay, AX is equal to 7AV1 plus 3BV2 plus CV3, so its length is the same as before. Now we want to maximize AX subject to x being a unit vector, but with a being equal to 0. So now we have to adjust ABC, satisfying this constraint, a square plus b square plus c square equals 1. But now we are forced to let a equal 0. So how can we maximize this? If a equals 0, right, we have 9b squared plus c squared. And we simply let b equals 1 and c equals 0. So we are left with 9. So the length of AX would be equal to 3 in that case. Right? And so that's what we do. So if we are constrained to force this coefficient of V1 to be equal to 0. So we are looking for an x which is orthogonal to V1 because its orthogonal projection along V1 is 0. And the solution is let B be equal to 1 and C be equal to 0. Okay, so now let's generalize this observation. So we want to maximize L2 norm of AX subject to x being a unit vector, but with alpha 1 being equal to 0. So the coefficient of x along V1 is equal to 0, or x transpose V1 equals 0. And the solution is make alpha 2 equals 1, and all the other alphas, alpha 3, alpha 4, and so on, equals 0. In other words, V2 equals argmax of, under this constraint, x must be a unit vector, and it must be orthogonal to V1. So we are looking for a unit vector that's orthogonal to V1. That would maximize the length of the projection AX. And the solution is V2. X is V2. And the length is L2 norm of AX, and that is lambda 2. When x is V2, we get lambda 2 as the length of AX. Okay? So this is the second eigenvector. And then, so let's look at what's happening geometrically. This is, on the left, we have a three-dimensional space of x's. Okay, so, and this is a unit circle. And since A is symmetric, the three eigenvectors, which are all unit vectors, by the way, are mutually orthogonal to one another. Okay, and so take any egg or take this sphere, unit sphere here. Okay, it maps to this three-dimensional hyperellipsoid. And the three axes, the major axis is along V1. The second major axis is along V2, and the third major axis is along V3. And the lengths are lambda 1, lambda 2, and lambda 3. Okay, and I'll demo this in Matlab in a bit. Let's see how much time we have. This lecture ends at 3:45. So we have a little over 15 minutes. That should be enough. Okay. Suppose the spectrum of the for 4 by 4 symmetric matrix is this 4v1. I just selected 4, 3, 2, 1 just for simplicity. Okay, so I have a 4 by 4 matrix A, and its eigenpairs are 4v1, 3v2, 2v3, and 1v4. And I want to find argmax of AX such that under these conditions, I want to find an X that maximizes the length of AX. Okay, but the length of X is square root of 2. And the projection of X along V2 equals 1. The projection of X along V1 equals half. This is my problem. I want to find such an X. Okay, so let X be alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 plus alpha 4 V4. Now, since the length of X is square root of 2, what is my, one of the restrictions is, oh well, let's go by this. So X transpose V1 equals half. What's X transpose V1 in terms of the alphas?
Alpha 1.
Alpha 1. So X transpose V1 equals 1 implies alpha 1 equals half. X transpose V2 is alpha 2. So alpha 2 equals 1. Okay. And the length of X is square root of 2. Therefore, alpha 1 square plus alpha 2 square plus alpha 3 square plus alpha 4 square should be equal to 2, right? The squares of all the alphas summed will give us 2, because the square root will give us this length of X, which is square root of 2. So we have alpha 1 and alpha 2. We can only adjust alpha 3 and alpha 4, right? What do? We let alpha 4 be equal to 0. And we let alpha 3 be whatever would meet this constraint. So we let alpha 4 be equal to 0. And so what's alpha 3 now? So we already found out alpha 1, alpha 2, and alpha 4. So in order to make the L2 norm squared equals 2, we must let alpha 3 be equal to square root of 3 over 2. Okay, so this is our solution. X must be plus minus half alpha 1, right? Well, actually, absolute value of alpha 1, it says that alpha 1 is half X.
Excuse me, Dr.
Yes.
Das.
Yes.
Could you repeat how could you take alpha 4 as 0?
Oh, because lambda 3 is more than lambda 4.
Okay.
Okay. Now, okay. Now, what happens is we want to maximize the amount of stretching. Let's take a three-dimensional case here.
Okay.
We want an X. Let's say X is a unit vector. We want to maximize a unit vector excuse me, we want to maximize the length of AX,
Okay.
okay, where X is a unit vector.
Yeah.
Okay, the solution is X is V1.
Uh-huh.
Okay,
Yes.
now suppose we want to maximize again the length of AX with X being a unit vector, but under the condition that X is orthogonal to V1.
Okay.
X must be orthogonal to V1. So what's such a unit vector, X, that maximizes the length of AX?
Hmm.
X must be equal to V2,
Yes.
in which case AX will be equal to lambda 2 V2.
Correct.
Okay, now we want to, well, now we are left with the third one as this is the smallest lambda 3. Okay,
Mm-hmm.
now what did we in fact do in the second case? So we are restricting our attention to vectors that are orthogonal to V1, right? So
Yeah.
between V2 and V3, since we know that lambda 3 is the smallest numerically, what we do is we let it equal to 0,
Yes.
right?
Yes. Yes.
And so that's exactly what I'm doing here. So that's why between V3 and lambda V4, since I know that this has a smaller, numerically smaller eigenvector value, lambda 4 is smaller than numerically what lambda 3. Therefore, that's what I do. I let alpha 4 be equal to 0.
Yeah. Okay. Yeah. Got it. Yeah. Thank you.
Okay, so that's my solution.
Yeah.
Now, this Quorum-Fisher theorem is something I'll leave as a little exercise. It's very trivial. Okay, now there we were considering the length of AX. Okay, now let's consider X transpose AX. Let's say we want to maximize X transpose AX, where X must be a unit vector. Again, you can easily see that it'll be lambda 1. V1, excuse me, argmax will be V1. Okay. And maximum value of this will be lambda 1. Now, if I want to maximize X transpose AX with the additional restriction, it must be a unit vector, X must be a unit vector, but I have the additional restriction that it must be orthogonal to V1. Then what should I do? Let X be equal V2. If I want to make it orthogonal to V1 and V2, then I must choose V3, and so on. Okay. Here, X is orthogonal to V1 and V2. That's the, basically, in a sense, what the Coulomb-Fisher theorem is. I use this in principal component analysis in another course. So now a review is fine. Let's rather do the, let me just briefly, for the sake of completion, do the review. So this is the matrix V in terms of the eigenvectors of the matrix A, and this is the diagonal matrix lambda, right? And this is what the spectral decomposition theorem says. Lambda equals V inverse V AV, or A equals VA V inverse. This is for any A, need not be symmetric, but for a symmetric matrix, V inverse and V transpose are the same. So it boils down to lambda equals V transpose AV, or A equals VAV transpose. Oh, A equals V, this is lambda, V lambda V transpose. And we also saw that this A can be expressed as a sum of rank 1 matrices. Each VI transpose is of rank 1. Okay. In fact, take any vector, let's say Z. ZZ transpose will be a matrix, but the rank of ZZ transpose will always be equal to 1. And you can clearly see why, but maybe we can do a little MATLAB demo. Okay, and then we saw all these properties. We can take a to the n, a inverse, and so on, a to the half, e to the a, and we all we have to do is this spectral decomposition theorem comes in very handy. This is lambda, right? And so all we have to do is carry out those operations on the diagonal elements of lambda. And then this is for symmetric matrices. We can represent any vector x as a linear combination of the eigenvectors because they are orthogonal and the coefficients are the alpha i's. So ax equals this. Okay. And length of ax squared equals summation of lambda I squared alpha I squared. And this is the geometric interpretation. We want to stretch, we use the eigenvectors, and I'm just going to shortly give you a demo. Meanwhile, are there any questions?
No, Dr.
Okay, so now let's go over to the Matlab code. Okay. Why am I here? Okay, I'm here. Okay. Now, this is my matrix A. Okay, and all I did was this. How I generated A was simply I took I took a random matrix, and then in order to make it symmetric, I added A transpose to it, and then I subtract 1 from it so that the coefficients lie between plus minus 1. Okay, and then I display it. Let me not, this one I tried it several times until I got a really good one. And now I actually have a small MATLAB demo. It's called map demo. I wrote it, I'll give it to you guys. Okay, so this is what it produces. It produces a figure. Okay, now, although it was a randomly generated symmetric matrix for visualization purposes, I selected this one because the one of the eigenvectors is very close to being the z-axis. Okay, so this red, this is v1 from 0 to either the bottom here or the top here is v1. And you see, this is a unit sphere. Okay, so I take the center of this unit sphere and join it to its surface. I will get a unit vector. Okay, and v1, v2, and v3 are these, and you can rotate these, and you can see clearly that they're mutually orthogonal, right? Because A is symmetric. Correct. So these are my three eigenvectors. I'll do it again because I rotated it once. Okay. Now, this is V1. I take any, if I let x equals V1, okay, so this AX will be this red from 0 to this bottom. And the length of this will be equal to 0.94616, which is in fact the, what is dA. So 0.94616 is the largest eigenvalue numerically, okay? And you see the maximum amount of stretching occurs here around this first eigenvector, this direction. And the direction remains the same. This is V1. If you take V1, the direction of AV1 is also lambda 1 V1. So it's the same direction as V1. Okay. And the you can see the length is of this is almost 1, right? Okay. Now I take any x equals V2 or negative V2. So I'll get either this 0 to this point or 0 to this point as AX, y equals AX. Okay, what's the length of this? I can do the rotation and I'll get, we'll see that, it's approximately 0.6, little less than 0.6. Okay, and this is the direction of minimum stretching, V3. And now in each case, if I let x equals V1 or V2 or V3, remember that the direction remains the same. If I take x as a linear combination, then the direction might change, correct? Okay, so, but lambda 3 is negative 0.37. So you see that the amount of stretching here, what's the length of this vector from the origin to this? About 0.37. Okay, and if we change the perspective here, we can see that. Do you see that? This length is approximately 0.58. From the origin, the middle of this, the center of this, not the origin, maybe, which is actually the center, the origin is the center of this hyperellipsoid, to this point here is 0.58, right? Likewise, on this side, it's 0.58 or 0.59. But changing the orientation this way, if I take it along V3, x is V3 plus or minus, what's this length of the blue line, this axis? It's less than 0.5, right? It's
0.37.
Yeah, it's actually 0.37. Okay, so this is the demo. And now let's take any x. So let me do it this way. This is A. Okay, let me use Eigs. I think Eigs would do it. Eigs A. Okay, so okay, okay, it has arranged itself numerically. Yeah, this is what I want. So what's my largest eigen value? Numerically, the largest is lambda 1 equals b 1, 1, right? Right? And lambda 2 is this. And lambda 3 is these are my 3 eigenvectors, and my eigenvalues were, sorry, these are my eigenvalues, my eigenvectors are v1 equals v all comma 1, v2 equals v all comma 2, the second column, v3 equals v all comma 3. Okay, so my eigenvalues are lambda 1, lambda 2, and lambda 3. Eigenvectors are v1, v2, and v3. v1 and v2 and v3, right? And now what's we can see that the lengths are 1. Norm V1, norm V2, and likewise for norm V, all the eigenvectors are unit vectors. What's their dot product? So the V1 transpose V2, what should it be equal to? 0, right? V1 transpose V2, because V1 and V2 are mutually orthogonal, it's approximately equal to 0. Numerically, so small, e to the negative 17, it's 0. V2 dot, sorry, V2 transpose star V3 is, again, so such a small quantity, it's for effective purposes, it's 0. And now V equals V1, V2, V3, right? This is my V. Actually, that's what we got. Now let's do the spectral decomposition theorem. What was A? Oops, sorry, you're looking at something very different. What was A in terms of V lambda and V transpose?
So it was lambda I, Vi, V
Not
transpose.
summation, just in terms of the matrices. A was equal to V lambda V transpose, right?
Yeah, V lambda V transpose.
So let's and lambda, let's call it L equals, well, it's the same thing as this D that we got. Okay, this D is actually our lambda. So what did our spectral decomposition theorem say? It was A was equal to V lambda V transpose. So let's do that. V star D, which is lambda, star V transpose, and we get this. Is it equal to A? It is equal to A. Right?
Yes.
Yes.
Now take any x. Let its coefficient be, let's say alpha equals um, 0.3, negative 0.5, and 0.2. So these are the coefficients. Okay.
Yeah.
Components of the vector x along v1, v2, and v3. So x equals, what do I do? So what was my v? This is my v. So x equals summation alpha I vi, right?
Yeah.
X equals summation alpha I vi. What do I do? V. Yeah, V. So x equals V star alpha transpose. So this is my x. Okay.
Yes.
What's the length of x? 0.6164. Now, what's the length of this? I told you that it's the same thing as alpha 1 square plus alpha 2 square plus alpha 3 square root, right? So what's that? Or let's do sum alpha square root of that. 0.6164, right? Which is the same as the norm of x. Okay. Now let's take y equals ax. A star x. What's the norm of y? 0.4154. But what are the lambdas? Lambdas are, let's do this. L equals diag of D. So this is the vector of all my eigenvalues. Okay. This is L1, lambda 1, this is lambda 2, and this is lambda 3. Now, the norm of AX, we know, is 0.4154. But we also know that it's equal to summation alpha I square, lambda I square, right? So, square root of that, square root of, how do we do the summation alpha I square, lambda I square? What we do is we have the alphas. Sum L dot star or summation of alpha dot. So I'm taking alpha square and lambda square, forming and then taking their element-wise product. Okay.
Square root of this, right? Square root of this.
I'll do it in 2 steps. Okay.
Okay,
So
okay.
this, oh, alpha. Oh, I see. Both should have been column vectors, so that's why. Point. So now let's take the square root of this. Point 4154. And that's also the length
norm
of
y.
Okay. So this is the Matlab code for the demo. You can either pass it a 2x2 or a 3x3 matrix. And then if you don't pass it an argument, then it will prompt for a matrix, and then we can read the code, and it finds the eigenvalues, eigenvectors, and it's basically, most of it is just fancy plotting commands. Okay. So with this, we end today's lecture, unless you guys have any other questions. Anything else you want to verify using MATLAB? Suppose A is not a symmetric matrix. Okay, then or minus 0.5, so that the coefficients are uniformly distributed between plus minus half. Okay. Now, the eigenvalues, eigenvectors in general will turn out to be complex quantities. Well, not in this case, but in general, they turn out to be complex quantities. And in any case, let's try another one. state. Yeah. Now you see you have some complex values here, right? The eigenvectors and eigenvalues have complex, they're complex. Okay, now let's go back to the 3 by 3. And VD was, okay, now it's all real. But now the eigenvectors, V1 equals V all comma 1. So I take the 3 eigenvectors. Okay, the 3 eigenvectors are not mutually orthogonal to one another. They are still unit vectors. Norm of, let's take V2, the middle one, it's equal to 1. But V1 transpose star V2, it would not be equal to 0. It's negative 0.05 or 0.06. V3 transpose star V1, 0.0772. So they're not mutually orthogonal because this is not a symmetric matrix.
So regardless of the matrix is symmetric or not, the eigenvectors will always have norm 1.
That's the convention. Remember, eigenvectors are all directions, right?
Yeah.
A star B1 is this, which is equal to these two are the same, right?
Yeah.
A V1 equals lambda 1 is this, V1. They give the same, right? Likewise, A V2 equals lambda 2 V2. So if I take, I replace V1 with, let's say, negative 2.5 star V1. Okay, now V1 is no longer an eigenvector, or no longer, excuse me, a unit vector, right? What's length of V1 now? It's 2.5, right?
2.5, yeah.
But you take A star V1 is this, and lambda 1, which is V11 star V1 is this. So again, it satisfies the property A V1 equals lambda 1 V1, right? So V1 is merely a direction.
Yeah.
And by convention, we choose all the V's, V1 and all the other V's, all the eigenvectors to be unit vectors. Okay? Okay, so any other questions?
No.
No.
Okay, so let's end today's lecture now.
Thank you.
And we'll meet on Thursday.
Thank you, Dr.
Thank you, Dr. Das.
You.
Thank you.